Okay, in this lecture, we're going to cover viscosity, surface tension, and capillary action. These properties that relate to intermolecular forces we covered in the previous lecture. Boiling point, melting point. We can also talk about those properties being affected by intermolecular forces, but we sort of did that in the previous lecture. Remember, intermolecular forces can be things like dispersion forces. They can be ion dipole forces, they can be hydrogen bonding, they can be dipole-dipole, right? It's just not a chemical bond. A chemical bond is an intramolecular force. Intermolecular forces are what hold, say, two water molecules together, not a single water molecule to its other atoms, right? This is a chemical bond right here. I'm talking about intermolecular forces, which is this hydrogen's attraction to this oxygen's lone pair over here in this water molecule. And it's this intermolecular force right here that is responsible for these properties: boiling point, melting point, viscosity, surface tension, capillary action. And in the previous lecture, we talked a lot about, well, as you increase the temperature, you're increasing the kinetic energy of the molecules to the point where this water molecule has enough energy to break free and leave this other liquid water molecule and enter the gas phase. That's the boiling point. So we've sort of covered that. So in this lecture, we're going to cover really viscosity, surface tension, and capillary action. So let's start with viscosity. And viscosity is a little counterintuitive. Something with a high viscosity has a really slow or low flow. There's a lot of resistance to it flowing, so it sort of oozes. Okay, so at low viscosity would be something that flows really, really freely. And so this resistance of a liquid to flow is really related to the ease with which molecules can move past one another. And remember, these molecules are always shaking hands with other water molecules in the case of water. And so we could have one water molecule here that is attracted to this water molecule over here. And the force between these two water molecules, this is the intermolecular force, this is hydrogen bonding right here. Now, viscosity is the resistance of this liquid to flow. So if I have a container with water in it and I tilt that container, right, the water sloshes past one another, it flows. And it flows because it can break this hydrogen bond and reestablish another one on the other side. Right, so these molecules tumble past one another, but there is some resistance to this original water molecule from moving. Why? Because it's perfectly happy with this hydrogen bond right here. And so there is this resistance for it to move that's dictated by this intermolecular force, in this case, hydrogen bonding. And so viscosity will increase, it'll resist flowing, the stronger these intermolecular forces become. So maybe it's not water, which has a fairly strong intermolecular force in a hydrogen bond. Maybe it's something like hexane, right? This is a big, long hydrocarbon chain. And the only force this is really going to have with other hexane molecules is dispersion forces, right? It's polarizable. It's going to interact with other hexane molecules through the dispersion force. And so there's going to be a resistance to it flowing when one hexane passes the other hexane, because a lot of these hydrocarbons can be polarized and the electron cloud can interact with the electron cloud on a neighboring hexane molecule. Now, what happens as we go down this table from hexane to decane and beyond is the viscosity is going to increase. And the viscosity increases, the resistance to flow increases. Well, just think about it from a size argument. This decane is this big, long, kind of floppy molecule that is going to be hard to move past this another decane molecule that is this big, long, floppy molecule, right? As this tries to get past this other molecule, it bumps into it, and there are dispersion forces that sort of keep them at bay and keep them from moving past one another. Now, hexane is half as big, a little more than half as big, right? But it's going to be easier for it to pass the other molecule, right? For it to slosh past the next molecule in the liquid phase. Now, all of these viscosities for all these hydrocarbons shown here are actually lower than water's. And the reason why is that this hydrogen bond right here is much stronger than a dispersion force, which is the only forces that these big long hydrocarbon chains have with one another. To give you a practical example, say you are used to water. You are used to water's sloshiness, right? You pour water in cups all the time. You intuitively have, grown up pouring water back and forth, sloshing it around. So you have some, inherent understanding and familiarity and some motor coordination built into you that tells you this is how sloshy the water will be. This is its resistance to flow. So since it's the most familiar liquid to you, you sort of understand its viscosity. But if you've ever tried to pour gasoline, I bet you spilled it on the first try. And you spilled it on the first try because it is a liquid you expect it to be like water, but its viscosity is so much lower. So gasoline down here is octane. It has a much lower viscosity than water. It pours, it sloshes much, much more quickly. So when you go to try to pour gasoline into a small container, maybe in a lawnmower or something, you're going to spill it unless you use the fine nozzle, which you definitely should, and then you might not, but it's much sloshier. So if you're trying to pour gasoline, inherently your body thinks it's water, and you're going to end up spilling it because it pours much more quickly and flows much more easily. It has a lower viscosity. Okay, so that's viscosity. Its resistance to flow will increase with the stronger intermolecular forces. So you could compare something like water with propylene glycol as well. Propylene glycol, actually let's look at glycerol. Glycerol looks like this molecule. It has some carbons, but it has these OH groups. And I'm going to draw it a little bit, the hydrogens off to the side here. It has these OH groups, and I'm illustrating this because I want to show you the lone pairs here on oxygen, and that I have a hydrogen bonding situation that can set up here with a neighboring glycerol molecule, right? So I could have a glycerol down here as well, and well, it has these OH units. And now I'm looking at the intermolecular force that is between these two glycerol molecules. And that intermolecular force is shown here in green, these 3 hydrogen bonding areas. And so now there's 3 handshakes that I have to break if I want one glycerol molecule to move past the other one, right? Whereas up here, there was just one in water. And so as the amount of hydrogen bonding sites per molecule increases, the viscosity will increase. And glycerol is this really high viscosity fluid, a large resistance to flow. It oozes, out of the container if you try to pour glycerol. Okay, so that's viscosity, one of the properties that is affected by these intermolecular forces. And so you can look at pouring water versus pouring gasoline versus pouring glycerol, and you now have this conceptual understanding of, why these things have higher resistance to flow or lower resistance to flow. It's because of these intermolecular forces and the different types of intermolecular forces that are present. The other thing I should briefly say here is that the viscosity depends on the temperature. Okay, so I should note that higher temperature means lower viscosity. Okay, because what you're doing is trying to overcome the intermolecular forces. And the viscosity is going to depend on temperature. The higher temperature means there's more kinetic energy to move past one another. So even if you still have these 3 hydrogen bonding sites, at higher temperatures, each of these glycerol molecules, right, is hyper. It's moving back and forth really, really fast. So these hydrogen bonding networks are not really set up as rigidly as they might be, okay, at slower temperatures, right? So imagine you're trying to, shake hands with 2 friends with each of your hands, right? And you both are standing next to each other. You can shake hands with both of your hands at the same time, or maybe with 2 different friends, one with each hand, okay? Now, if you're running by them and trying to, grab onto them and hold onto them, you're at a much higher temperature. You're not going to be able to grab hands as easily. So you're going to keep, bouncing off one another or running past each other. You're not able to establish that firm grasp. grasp. So at higher temperatures, you will have a lower resistance to flow because you're not able to set up each of these, strong hydrogen bonding networks like you would be able to at lower temperature. So that's viscosity. Surface tension, another property that is affected by these intermolecular forces. And surface tension is the amount of energy required to separate waters, in the case of water surface tension, waters at the surface, right? But it's really the amount of energy required to separate a liquid molecule from another liquid molecule at the surface. Now, water has a amazingly high surface tension. And again, it's because of this intermolecular force, this hydrogen bonding that is holding waters together, resisting separation. So if you wanted to think about a glass of water or a lake of water, as perhaps is shown there, right? You have this container and you have all of these water molecules. So instead of drawing out the H2O, right, I'm just going to draw a bunch of water molecules as circles here, not as oxygens. Should have drawn a smaller container. And now let's look at the forces that are on, say, this water molecule right here. The force on this water molecule is, well, it's hydrogen bound to this water molecule. It's pulled to the left, but it's pulled to the right from that water molecule. It's pulled up from the water molecule above it, but it's pulled down from this water molecule here. So any interior water molecules have this net balancing of forces because there's waters on all sides of it. Now, if I look at this water molecule here at the surface of my container, it's pulled to the left here, it's pulled to the right here, it's pulled down here. There is nothing above it pulling up. So there's a net force here down on this water molecule. And so the net effect here, I've exaggerated it, but the net effect here is that all of these waters at the surface up here, right? There's just air above it. There's no real net water molecule that's pulling these waters up. There's a net force down for all of these water molecules. Let me erase some of these. All of these water molecules, there's a net force down. Okay? And what this means is that these water molecules actually at the top get compressed. And what'll happen is you actually have these water molecules. Let's redraw this now that we've taken account of these forces. You get these water molecules that have this uniform, close packing at the top. Whereas within the liquid water molecules, there's actually a lot more freedom of rattling around because there is no net force. And so it's exaggerated here, but some are spaced a little bit more apart. They're rattling back and forth. They're bouncing off because there is no net effect on any one of these water molecules like there is at the surface. And so what you end up getting here is actually this fine skin across the surface. And you can also see this in a droplet of water too, right? That it beads up. We'll get to that in a second as well. But the net effect here is this skin of water. It's almost like you have a water, rubber membrane across the top of this water. And this is the result of these net downward forces. Okay, but that's really only going to happen with a strong intermolecular force, that you're going to have this strong membrane, this skin forming on the surface. And so water has a pretty high surface tension because exactly of these strong intermolecular forces known as hydrogen bonding. And so you get this surface because of the hydrogen bonding, and it's holding the waters together and it's resisting separation. Remember, each of these water molecules are holding on to their neighbors too. So you get this really, really tight skin that is strong to resist these other forces, right? If you're a water bug on the surface of this, and well, if your leg is shaped like this, yes, maybe you can pry apart these two water molecules. But if your leg is sort of shaped on like this, Well, now there's not a ton of force in one particular area, right? Remember, pressure is force divided by an area, so you're not exerting that much pressure between these two water molecules anymore because your leg is flat and this force of your body weight is dispersed over this skin. Now, a human is much, much bigger, so it's not difficult for us to dip our hand in here and overcome this water-water intermolecular force. But for a very light water bug shown here, it has its force spread out over this area, and the pressure on any one particular hydrogen bond is not great enough to overcome this surface tension. So that's surface tension, that's viscosity. We'll pause here and do a practice problem about these two concepts. So maybe take 30 seconds and think about how you would answer this problem before we move on. All right, so how do viscosity and surface tension change as intermolecular forces of attraction become stronger? How do they change as the temperature increases? Okay, so you would expect as the intermolecular forces get stronger, well, the surface tension, that skin, is going to be stronger. Okay, the resistance to flow should become stronger as well. As the force gets stronger, both of those properties should get stronger. So both viscosity and surface tension should increase as intermolecular forces increase. Now, we know as temperature increases, you're not able to set up these intermolecular forces as often. And so these properties that are manifestations of the intermolecular forces themselves should go down as temperature increases. So the correct answer here should be C. Both viscosity and surface tension increase as intermolecular forces increase, and both decrease as temperature increases, right? Because both properties are related to these intermolecular forces. So there's a direct relationship. As the forces get stronger, these properties get stronger. Temperature overcomes these intermolecular forces, doesn't let them take hold. So as temperature increases, you have less intermolecular forces, and so both of these properties get weaker. So the correct answer there should be C. The last property that we're going to talk about here is cohesion and adhesion and how it relates to capillary action. This is probably my favorite property because it's really a balancing of two different types of interactions. First, let's think about cohesion. Cohesion is what we've talked about thus far in terms of hydrogen bonding. So we'll go back to our friendly example of the water molecule. And this intermolecular force that sets up to this neighboring water molecule, this right here is a hydrogen bond, but this is a cohesive force or cohesion. Okay, intermolecular forces that bind similar molecules to one another are called cohesive forces. So both adhesive and cohesive are still an intermolecular force. It's just when it's like on like, it's cohesion, right? These are collaborators. They're the same molecule. It's a cohesive force. Now, adhesion is going to be when you have, say, glass here, and one of the oxygens in this glass molecule is attracted to the hydrogen on this water molecule. This right here is adhesion. Right? So intermolecular forces that bind a substance to a surface are called adhesive forces. So the molecules are different. The molecule in glass is a silicon oxide. The molecule of water is hydrogen and oxygen. And so this is adhesion versus cohesion. Now, we're going to see capillary action in a second. It's the balancing of these forces that lead to capillary action and why plants can exist. But let's dive a little bit deeper into exactly the type of force that is happening here in adhesion. So instead of just writing glass, this is chemistry after all, let's look at the actual molecular view here that is happening. And let's look at this as this silicon oxide framework. And this is SIs and Os sort of repeating pretty much, forever here. And these oxygens have 2 lone pairs. These oxygens at the top have 3 lone pairs. Okay, so this is glass, or meant to represent glass down here. And this is a water molecule that is interacting with glass. Now, let's look at pound for pound the force here of this attraction versus here. Cohesion versus adhesion. Now, this H right here that is bonded to this oxygen is basically just like an H+. And the reason why is because this oxygen is hogging all of the electron density in this bond. And so what happens is, this hydrogen that is chemically bound here, all of its electron density is over by this oxygen. So this is like a flat proton waiting here. And this flat proton is seeing 1, 2, 3 lone pairs on this oxygen. Whereas this hydrogen right here, that is basically an H+, is really just seeing 1 and maybe a little bit of a second lone pair on this water. 3 lone pairs, 6 electrons, are greater than 4 electrons. So for water, we'll make the comment down here. For water on glass, adhesion is going to be stronger than cohesion. And so it's a balance of these forces that is really important here, right? Which one wins out? And it depends on the 2 things you have, right? Is the force between water and another water stronger or weaker than between water and glass? And for this particular system of water and glass, the adhesion, water to glass, is stronger than water to water. And so what we end up seeing, and you guys have all seen this, if you take a thin tube of glass and you put liquid water in it, which we all have done, you get this. This separation between the 2, water and air above it. And you get this meniscus that is curved downward from the edges. And so we can see these observations in nature, but now we can explain them. And we can explain them by noticing that the adhesion is stronger than cohesion. I don't know why I wrote adhesion is greater than stronger. Adhesion is greater than cohesion. That makes slightly more sense. So the adhesion forces are stronger than cohesion, right? Which means if you're a water molecule, right, and you're sitting right here, right, you have the opportunity to go down here and be with your other water molecules and develop these kind of cohesive forces, or you can stay up here on the edge and stay on the glass because you're with this stronger adhesion forces. And so you get caught up on the glass, and at the glass-water interface, that force is stronger. Gravity is pulling all of this net water downwards, but in the middle, there is no glass for the water to hang on to. And so there is a net dip in the layer of water. Now, where I get near the glass, well, there's all these waters hanging onto the glass, and so they resist gravity because of this stronger force, and they resist more strongly than the waters in the middle. And so you get this downward-facing meniscus because adhesion is stronger than cohesion for the water-glass pair. Now, you can think about other types of interactions. Just to draw again, adhesive forces attract the liquid to the wall of the tube. Cohesive forces attract the liquid to itself. Water has stronger adhesive forces with glass. So this is the example of water in a glass tube. We get this downward facing meniscus. This is water glass, right? This is because adhesive wins out over cohesive. But now let's look at a different substance. Let's look at something toxic. And let's look at the mercury glass system. Mercury doesn't have hydrogen bonding. There is nothing that wants to bind to the oxygen lone pairs in glass. So mercury actually only has dispersion forces with itself, and it really isn't pulled onto glass any stronger. And so really for mercury, the adhesive, it doesn't want to get with the glass. There aren't strong forces here. Adhesive is weaker than cohesive. And so here, the mercury-mercury interactions are stronger than the mercury-glass interactions. And so you get this shape for mercury, right? The upward curving meniscus. Why? Because these mercury molecules right here, all of these mercuries are pulled down by gravity, but these in the middle, right, are in a more beneficial standpoint. They're near other mercuries than they would be here on the edge. That would be much weaker, so they're dragged down by gravity more strongly. Or I should say that force is easier to overcome than the forces here at the middle. So this is mercury in glass, and if you have ever used a mercury thermometer, well, you're probably a little bit older because they're toxic and not really used anymore. But in mercury thermometers, you'll see this, bowing out of the mercury, and it's shrinking away at the interface with the glass, where water does the exact opposite. Okay, so the meniscus curves up from the edges when it comes to mercury. And, all this cohesive versus adhesive forces governs a lot more interactions you can think of in your car. Actually, I should probably draw it with a windshield since that's really what I want to show here. Okay, this is you. You're really cool. You're driving down the road and you know something about chemistry. And you know that living in a climate where it rains a lot, it'd be really cool if the water, didn't splash and stay on your windshield. Yes, you have windshield wipers, but that takes some time. And you don't have time for that. So what you do is you develop a compound that coats the surface of your windshield. And so it coats the surface of your windshield, I'll enlarge it here, in something that is nonpolar. So if it's something that's nonpolar, that isn't going to have these dangling oxygen bonds, then when water interacts with this surface, water has a couple of options. It can splatter and cover a large portion of this surface, but it will only do that if the adhesive forces are greater than cohesive, right? This example here, the water is hanging on to the sides of the glass because those dangling oxygen lone pairs are attractive to water. But you've covered your glass in this film, right? You've covered it, and I'll make it a different color so it's here easier to see. You've covered your windshield now with this non-polar coating such that there's no dangling oxygens with lone pairs. So now when the water comes and has the option to splash onto your windshield, well, it's not going to do that and take up a lot of space. Why? Because there are no beneficial adhesive forces. There's no hydrogen bonding ability. And so instead what the water does is tries to minimize that interaction. And so all the water molecules stay near the other water molecules, and you get this beating up of the liquid water. It maintains this spherical shape because it's minimizing this interaction right here between polar and nonpolar. It's minimizing the adhesive forces and it's maximizing the cohesive. Why? Because the adhesive here is really weak with nonpolar. The adhesive here is strong because there is not a nonpolar coating. There's a glass molecule, there's oxygens with lone pairs holding on to that water molecule really, really strongly. But now that I add Rain-X, or another nonpolar compound, to my windshield, well, now I've taken away those dangling oxygen bonds for the water molecules. I'm nonpolar. I don't have anything for the polar water to really get attracted to, so the water stays beaded up. Okay, and the net effect is the water doesn't stay there, adhered. It's on a surface that is inclined, and the water molecules roll off the surface. And so this is the effect you see when it starts raining on your car, and you're a smart chemist, and you buy the Rain-X, or you make something at home because you're clever enough. You can coat your windshield with one of these compounds such that the water molecules bead up, roll off, and keeps your windshield clean. So that's another real-life application of understanding conceptually this balancing of forces. The last one I want to talk about here that's cohesive versus adhesive is capillary action. And capillary action is the effect, well, actually, let's do this first. A practice problem on the inside surface of the glass tube, if it's covered with wax instead, which is a nonpolar hydrocarbon, how does the general shape of the water meniscus change? Okay, so let's take 30 seconds and think about this in terms of the intermolecular forces, adhesion, cohesion. Let's take this glass tube, and instead of it just being glass, let's coat it with wax, a nonpolar hydrocarbon. What is the general shape of the water meniscus? Try to draw it now. Time's up. Okay, so now we're taking this glass that was in black and coating it with this hydrocarbon, nonpolar, and now I'm going to pour water into this tube. And it's going to look exactly like the mercury example. That was pretty poor. It's going to be this meniscus that is curved like this, right? Again, because it's going to minimize all of these nonpolar-polar interactions here, and it's going to maintain these polar-polar interactions amongst the water here. So this should look much like the mercury example, not like your classic water and glass example, right? Because here adhesive is weaker than cohesive now that we've coated it in wax. And you can do this experiment at home, actually. Okay, the last thing to talk about here is capillary action that I just want to illustrate with a series of tubes dipped in water. And capillary action is this result of these adhesive versus cohesive forces. So let's again assume we have water in this container, and I'm going to take this tube, that is a thick tube, and stick it down into this container. Okay, now, if this is a glass tube, which I'm going to tell you it is, right? We know the adhesive forces outweigh the cohesive forces in the glass water system. So ad is greater than co. So what we'll see when we dip this glass down into this liquid water bath is that these liquid waters, right, that are suppressed and kept down by gravity and air pressure, well, now they see some beneficial force they have access to. And so if we zoom in right here at this water glass interface, right, what we see is this water molecule that for the first time is seeing something besides a water molecule. And what is it seeing? It's seeing this dangling oxygen with 3 lone pairs off of this silicon oxide, which is glass, surface. And these 3 lone pairs here are much more attractive than the 2 lone pairs of this other water molecule down here that it's used to seeing. And so there's actually a net force up. And so what we'll see here is that this water near the edges, right, will start to climb up into this tube. And, you know, it won't be really a lot, but it'll be a little bit higher than the rest of the dish. Okay? Because there's still a pretty large amount of water molecules here that are, you know, pushed down by gravity, but it does, you know, peak up a little bit into the tube. Okay? But let's use smaller and smaller tubes, right? And let's use tubes that are this thick. Now we put this tube in this container, and the liquid water molecules go up to here. Right? Why? Because in this general region where the same gravity is pushing down, right, there's a higher ratio of water molecules at the edges than inside the middle. Right? Here, most of the water molecule in this whole area, right, pressure is a force over area. Well, over the surface area here, right, gravity is the same force, but it's a larger area over here, right? And so these water molecules at the edge represent a very small number of the total water molecules in this area. But as I make this tube that I'm drawing in 2 dimensions, but try to think in 3 dimensions here, there's a surface going all the way around here in this tube. All the water molecules around the surface of the tube are seeing this beneficial net upwards force, right, that are able to balance this downward force of gravity. And so what happens is I can make this tube really thin, and now I'm really creating a ton of liquid water molecules that are exposed to these silicon oxide dangling lone pairs of oxygens compared to the water molecules in the middle of the tube. And so what you'll see is, you know, as you make these tubes thinner, the water level rises. And again, the reason is because the proportion of water molecules that are interacting with the surface, right, is now much, much greater compared to the waters in the middle of this tube, right, versus the waters here looking at this cross section of surface. There's only a few water molecules at the edge compared to all these in the middle that aren't having any surface water interactions. And so there's not as many forces pulling up, so gravity is the same force pulling down. It doesn't get as high as it does over here, where there's a whole lot of beneficial up silicon oxide water forces to counteract the gravitational force going down. So this is capillary action. As you make this capillary, which is a really, really thin tube, as you make the tube really thin and approach a capillary size, then you get the water going higher and higher and higher. And this is how plants are able to survive. And plants' capillary action allows water to move up through plants against gravity, right? How does, you know, this tree that is gigantic, right, and has leaves way up high, how does this leaf right up here actually get water and nutrients to it? It's because these plants have evolved to maintain these really, really thin tubules that go all the way down here so that when it rains and there's water in the soil, they can draw up water into the leaves at the very top of the plant just due to this beneficial adhesive force of water versus the cohesive force. Okay, and so that's why plants exist. That's why humans exist. The answer to everything in life itself is capillary action. So on that note, I think we'll end this lecture. Next time, we'll look at supercritical fluids and get into phase diagrams. But that'll do it for this lecture. See you next time.